given A belonging to 2 by 2, we decompose A into its, let's write the conformal first, conformal part, and the anticonformal part. Everything is in 2 by 2. This decomposition is unique. Well, these things, the conformal and the anticonformal in 2 by 2, they are subspaces, they are orthogonal subspaces, and that gives us some powerful things as we're about to see, okay? And we're interested in functions that have the following property. So quasi-regular, mappings. I'm going to write f from omega goes into R2, or from domain in R2 into R2, such that we have that these guys belong to Sobolev space W1, 2, and we have the following identity for the gradient, that if we take the operator norm of the gradient squared, then this is less than q times the determinant of the gradient almost everywhere. No? So in particular, we're interested in matrices, let's call them A again, in 2 by 2, which have the property that when we take the operator norm squared, it's less than the determinant of A. Okay? And let's try and understand the implications of that in terms of the conformal and the anticonformal and the Beltrami coefficient. So also recall the Beltrami coefficient. So I should say this is not entirely standard notation, because typically this is done in the context of complex numbers, and we'll see how it's equivalent, but it's much more easy to see what it says initially if you first think about this in 2 by 2 matrices. So the Beltrami coefficient we've defined as follows. So of a matrix A belonging to 2 by 2 is given by the following, that we take the anticonformal part, we reflect it to get a conformal matrix, and that is equal to this conformal matrix mu of A times the conformal matrix part of this thing. Okay, so let's write it u of A, and just remind that I is this reflection, 1, 0, 0, like this. You know? And we saw that this makes sense because this thing turns this into a conformal matrix. So we can just define this thing to be this conformal matrix composed with the inverse of this one, and it is a conformal matrix, and it's well defined. Yeah? Cool. All right. So let us do some bit of linear algebra and see what we get. So first, let's look at this thing. So note that the operator norm, which is equal to the supremum of A of V, V belongs to S1. This is less than the Hilbert-Smith norm, like this, which is just all the entries squared, square rooted. You know? And this thing we can understand very well in terms of the conformal and anticonformal decomposition, because these are orthogonal subspaces. So this is an orthogonal decomposition of this matrix. So we think of the matrices in 2 by 2 as a 4 vector, then these guys are orthogonal decompositions in 2-dimensional subspaces, right? Because we saw that the inner product between a conformal and an anticonformal is just 0. You know? So if we take just the Hilbert-Smith norm squared, then that's the same as the norm of the conformal part squared plus the norm of the anticonformal part squared. Are you all happy with that? Yeah, thumbs up if so. And if not, just tell me, I'll add. We have time, I can put as many details as you want. Okay, super. So, we have that this is true. We also have a neat identity to do with the determinant. So, you know, the determinant of A is equal to the determinant of the conformal part and the determinant plus the determinant of the anticonformal part. So, as I said before, this is wildly untrue if you have a typical decomposition of A into matrices, whatever, A1 and A2. Right? This is a highly nonlinear thing, determinant. However, it does happen to be true when we break things up into conformal and anticonformal. And that's a little bit of algebra, but it is in some sense intuitive in the sense that I tried to say some words about this last time and I don't find good words. Okay, whatever. This is algebra. So what I wanted to say was that the positive part of the determinant, well, let me say this. The conformal part has got positive determinant. The anticonformal has got negative determinant. So you can sort of anticipate that these things are doing quite different things. So this decomposition is not entirely a surprise, just based on that. The way that the conformal and the anticonformal affect this thing is not. It doesn't seem completely strange that we can just take the volumes as additive, because this is like the negative area and this is the positive area. Those are the only words I have. But anyway, it comes down to linear algebra. If you just want to verify this is just a true fact. Okay, cool. So let us continue to try and understand this. So we also know that if we take the determinant of a conformal matrix, so something like this, A minus B, B, A, what's that? That's A squared plus B squared. Yeah, which is the same as the Hilbert-Smith norm squared, but multiplied by 2, because we're going to get a 2a from this and a 2b. So what I need to do, so what I should say is actually divided by half. Not multiplied by 2, but divided by a half, right? Because we're going to get an a squared. Yeah, so if we have an a squared and another a squared and a b squared and another b squared, so the Hilbert-Smith norm divided by 2 exactly gives a squared plus b squared. Yeah? Cool. So looking at this, I mean, the same calculation works if we have an anticonformal. So if we have instead of this, we have this, it's still exactly the same, right? Still exactly the same calculation. So in this thing here, instead of writing determinant, we could put, we could do the following. So that means the determinant, and I need to write it again. That means we can just replace this by a half of the Hilbert-Smith norm and this by half of the Hilbert-Smith norm squared, right? So this is a half of A of c squared plus a half of A of the anticonformal thing squared. Yeah? All right, now, if we look at the Beltrami coefficient, let's take the determinant. All right, thank you for this. I think that's correct. I'm sure that's correct. Thank you very much. Yes, minus. Yes, good job. Yeah, because this is a negative determinant. All right, so if we look at this line here, let's take the determinant throughout. So call this thing star. From star, then we have the determinant of A like this is equal to the determinant of mu of A C like this. And determinants, of course, we we can do like this. We can do determinant of u of a, and then determinant of this thing. So you like this, yeah? All right, so this thing now has positive determinant, right, because it's multiplied by reflection. So this is the same as having a half of this guy squared is equal to a half of u of a over split norm squared times a half of the conformal part squared, yeah? Just using this. And note, this time this is the correct sign because determinant is multiplied by reflection to make it positive, yeah? And reflection is not going to change anything about this little identity here, just, yeah? Cool. So let's get rid of some of the halves. So this is like a quarter and this is a half, so let's do it like this. We have 2 is equal to this times this. Yeah. Cool. So we can start to put things just in terms of the conformal matrix, right? So that means the determinant of A, let's pull out the factor of a half like this. It will be equal to the conformal matrix squared, oops, over split norm, minus this stuff, right? Minus u of a squared, again, the conformal part of this squared, like this. Let's factor out the conformal part. The anticonformal part is this thing divided by 2, right? So it's this thing divided by 2. And then let's factor out some constants. So we have this. Like this, yeah? And that is to understand the determinant in terms of the Beltrami coefficient and the conformal part. Now let's understand the norm squared. And the norm squared of A is the norm of the conformal part squared and the anticonformal part squared. Okay. And then we are going to use this identity here, and then this is the same as the conformal part squared plus 1 over 2, the anticonformal part squared, then this thing, and then we'll pull out the conformal part. So we're going to have the conformal part squared. We have 1 plus u. U of a squared over 2. So let's put it in here. So if we try and understand, so anyway, okay, so if we look at this, then if we write, so what we require is that the operator norm squared is bounded by some constant q times the determinant. So since the operator norm is bounded by this, that means that this thing squared is less than q times the determinant of a, right? And then we put in this stuff. So that means that we have over 2, yeah, is less than equal to q over 2 times this thing. Oops. Like this, yeah? So in terms of the conformal matrix and the Beltrami coefficient, these things are equivalent, yeah? So we're going to divide through by the conformal matrix. Let's divide through by the norm of this thing, okay? So we'll square it so we don't have it anymore. So then we have that 1 minus UA squared over 2 is less than q over 2, 1 minus, oops, the other way around, we have this thing, 1 plus is less than this thing, over 2, yeah, let's divide through by this thing and we have this expression which is relevant 1. Oops. Okay, is less than q over 2. And what we wanted was q to be some finite number. Yeah? We wanted q to be some finite number. If we're talking about q quasi-regular mappings, it's a fixed finite number. And then from this identity, we see that that would be equivalent to insisting that mu of a is strictly less than root 2. So if this thing is strictly less than square root of 2, then this actually will be true. And we will have that the matrix A satisfies this. Oh, I'm so stupid. Satisfies this, you know? And we can take Q to be equal to 2 times this thing, right? Oops. Like this. Yeah? So another way to insist on having a matrix A, which is the kind of matrix that will occur as the gradient of a quasi-regular mapping, is to insist that when we take the Beltrami coefficient of the oh, I see perhaps the issue that this is absolutely correct. That when we insist that the Beltrami coefficient of the gradient is less than square root of 2, then this is some constant that is strictly uniformly bounded below, above by something, right? Because this thing is strictly bigger than 0 if this is true, yeah? And this thing is strictly bounded above by 4. Yeah? Yeah? So insisting that this is true is equivalent to the existence of some Q for which this is true. Yeah? And if we say that we're considering a family of matrices for which this is true for some universal bound, so for example, that this is, if we had that this, I'm going to keep it like this, but if we took a family such that we have this, yeah, then there would be a universal upper bound on the Q for every A inside that family. Do people see what I mean? Yeah? Cool. So that's going to allow us to reformulate the condition of being quasi-conformal for gradients in terms of the Beltrami coefficient. And again, the relevant thing is that the Beltrami coefficient is strictly less than root 2 in order for this to be a strictly finite number. Yeah? Cool. So I'm going to erase the board. Keep that in mind. So the reason we have this root 2 rather than the 1, which you might expect if you've seen the Beltrami equation before, is because we are doing this in 2 by 2. And when we take the Hilbert-Smith norm of the matrix, it gives us a different constant. We're going to talk about now what is called the Wirtinger derivatives for complex functions. And I don't know how to spell that word, so I'm going to write just Wirtinger derivatives, which you might have seen before. Okay, so we're going to talk about functions from subspace in the complex plane into the complex plane, but these are not holomorphic. These are very much not holomorphic. So we're very used to thinking about these functions when they're holomorphic. We don't have holomorphic functions now, okay? Just that they belong to W1, 2. Okay, so they have a weak derivative that exists in the Sobolev sense, okay? And we're going to consider the following things, this d by dz, which is d by dx, or half d by dx, minus a half d by dy, and this thing, d by dz bar, which is defined to be a half of d by dx plus I d by dy. Okay? And we're going to do this typical thing of writing, we've done this a million times, of writing this. Okay? For these functions, u of x, v of x, and of course these guys belong to Sobolev space in the natural way. These are just functions from R2 to R. No? And then we can apply these operators to this thing. So what we mean by df by dz is applying the partial to both of those guys with respect to x, minus I, the partial with respect to y, with a factor of a half in front. Yeah? So let's write out and see what we get. So we have a half. Let's do the dx first. So I'm going to have dx plus I dx. Just doing the dx thing first. And then minus dy plus I v dy. And then let's collect up the real and imaginary parts. So what do we have for the real? We have a half of u of x minus u of y. Okay. That's already wrong. Oops, yeah, because it is minus I, like this. Like this, yeah? So collecting up things, so this is the Wirtinger derivative. So collecting up things, so we have minus I times I, which will give us positive, so we'll have this. And then collecting up the i's, we're going to have like this. We're going to have I of x, and then we're going to have minus u of y, right? Or v of x minus u of y, like this. No? And let's do this guy, df by dz bar. 1 over 2, same procedure. This is now this guy. We're going to take the x, so we have u of x plus I, v of x, and now it's plus I, and then we do the y, right? And again, this is plus, so we're going to have u of y plus I, v of y. And then collecting up the real and imaginary parts, we are going to have I times I, so it's going to be u of x minus v of y, like this, and then we're going to have this I of v of x plus u of y, like this. Yeah? Cool. Now, these are complex numbers. Let's make the identification that if we have a complex number a plus ib, I'm going to put a bracket m around it, and then that's going to be defined to be this matrix A minus B, B, A, like this. Yeah? Because this is the field homomorphism, as we've talked about, all the algebraic things for this hold exactly the same true in exactly the same way they hold true for this thing. But we get a different constant when we consider the norm, because when we do this, let's square it. Oops, m on the inside. Then it is this thing. So it is a squared plus a squared, b squared plus b squared. So we're going to get this thing. We're going to get 2a squared plus 2b squared, which is equal to 2 times what we'd have if we just took the absolute value of the complex number, squared. In other words, when we take the norm of the conformal matrix we create out of a complex number, then we're going to pick up this factor of square root of 2, which is where this square root of 2 thing was coming in before, right? Yeah. So when we do this identification of a complex number to a conformal matrix, then the norm of the conformal matrix is root 2 times the norm of the complex number. Yeah? Cool. All right, so let's turn these complex numbers into matrices and see what we get. So considered as a matrix will be the matrix which is like this. It'll be a half. It'll be ux plus vy, and then minus v of x minus u of y, and then v of x minus u of y, and u of x plus v of y. Yeah? That's what this guy will be. And this guy, z bar, will be, running out of space a little bit, will be just reading off like this. It's going to be u of x minus v of y. It's going to be minus v of x plus u of y. It's going to be v of x plus u of y. And it'll be u of x minus v of y. Yeah? Just like this. Yeah? And this is a conformal matrix, of course. Yeah? This is a conformal matrix, of course. But you should recognize some cool things here. So in particular, if we take this thing, df by dz bar, and then we multiply it by this reflection, 1, 0, 0, minus 1, then it is this u of x minus v of y. It is going to be v of x plus u of y. It's going to be v of x plus u of y, and then minus u of x minus v of y. No? And I'm missing the factor of a half because it's Friday morning. Yeah? Cool. Now, where have we seen stuff like this before? Where have we seen stuff like this before? Does this structure seem familiar to you? What happens if we add these two things together? So if we add the first coordinate, the 1, 1, we're just going to get u of x, right? Because there's a half u of x plus a half u of x. What happens when we add this together? What are we going to get? Just u of y, right? Yeah, because the v of x is all cancel. Yeah? What happens when we add this together? We're going to get just v of x. Yeah? And if we add this together, we're just going to get v of y. Yeah? Yeah? So adding this with this gives us the matrix of the matrix of partials that we would get if we turn this thing into a function from R2 to R2. So letting f tilde of x comma y be defined to be equal to u of x y, v of x y, this is standard way to turn something which is from complex numbers to complex numbers into R2 to R2, then we see that these two guys added together gives us a gradient. So let's, we don't do that. Let's just write it again. Then we have df by dz as a matrix plus df by dz bar as a matrix with this reflection. I've defined this already. This is the reflection I. This is the same as the 2 by 2 matrix, which we get from this function f tilde. Yeah? Cool. And what kind of matrix is this? It's a conformal matrix. Yeah? And what kind of matrix, I should have said, what kind of matrix is this? It's a conformal matrix. And what kind of matrix is this? Now you tell me, what kind of matrix is this? It's anticonformal. So what we have is the decomposition into the conformal and anticonformal parts of this guy here. Right? So this is the same as this thing, conformal, plus this thing, anticonformal. Huh? So that gives us an understanding of the meaning of these Wirtinger derivatives. Yeah? So this guy, df by dz as a matrix is equal to this thing like this. I'm wondering if I'm missing a factor from something. No, I think everything is cool. So yeah, this thing is this thing, because we're not talking about the norms yet. And this thing multiplied by reflection, I, is the anticonformal part. Yeah. And this reflection, if we compose it with itself, it's the identity. Yeah. So that would be the same as writing like this, as taking the anticonformal part and composing with the reflection to turn it into conformal. Yeah. Cool. So this allows us to reformulate our Beltrami coefficient now as a complex number, which is the standard way it's done. So let's try and squeeze that in. So Beltrami coefficient we defined like this, right? We went df tilde a reflection is equal to mu of a df tilde conformal, this thing mu of d of f tilde like this. Yeah. And now we're going to turn this into something which is a relation between complex numbers. So we're going to have that from this line here. So this is matrix multiplication, but as I said before, matrix multiplication exactly the same as complex numbers being multiplied. So turning this directly into complex numbers, we're going to have that this complex number is equal to some complex number, which we'll define in a second. Let's write it as mu, let's write it as nu of f. So nu of f times this complex number, which is df by, this is z bar, and this is df by dz, right? Where this guy, when we turn it into a matrix, becomes this guy. And instead of writing df, I just write mu of f because it depends on f, and I don't want to put too many symbols here, right? Yeah. So this becomes our Beltrami equation, our Beltrami coefficient, and our Beltrami equation when written as complex numbers. Yeah. And it's a neater formulation. It looks neater, yeah, but it means exactly the same thing. Yeah. This Beltrami coefficient is exactly encoding the relationship between the conformal and the anticonformal part of the gradient. That's what it does. And that's what we'll need. And in particular, what it does is it records the way the unit ball is deformed in terms of shape, but not in terms of size, and not in terms of where it's rotated around, right? It records the shape of the ellipse and nothing else, yeah? And U of F is the standard Beltrami coefficient. Yeah. And then this thing is what is known as the Beltrami equation. So if you type in Beltrami equation, you'll see this equation in many, many, many places. And what we are interested in is quasi-regular mappings, right? For which we have that this guy here has got norm less than, strictly less than root 2. Yeah? In order for f tilde to be a quasi-regular mapping, we require the Beltrami coefficient to be of norm strictly less than root 2. Yeah? So if we insist that mu of d of f tilde is less than, say, little kappa, where kappa is strictly less than, so that's right, it's almost everywhere, than square root of 2. Yeah? Then let's identify this stuff. So this thing is the same as this thing. So this is equivalent to the norm of this guy, this Beltrami coefficient turned into a matrix, is less than kappa almost everywhere. But when we do this, when we turn this into a complex number, we pick up this root 2 factor. So this is equivalent to, just as a complex number, mu of f is, actually let me write neither things. Let me write this as like 1 minus delta root 2, almost everywhere. And then this thing is equivalent to this being less than 1 minus delta root 2. And then just by this scaling factor we pick up when we turn a complex number into a conformal matrix, this is equivalent to this being what, less than 1 minus delta. Yeah? Yeah? So when we do the complex number formulation of Beltrami equation, or the complex variable formulation of Beltrami equation, what we insist on is that this guy is strictly less than 1 almost everywhere. And if we do that, then we actually have that this guy is this guy f tilde is a quasi-regular mapping. But the identification between f tilde as a function from R2 to R2 and f as a function from complex numbers to complex numbers isn't made if you look in these kind of books. They just do this automatically. So they'll say blah 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 quasi-regular mapping, and then they'll talk about complex functions from a domain of complex numbers to the complex numbers without anything. But you have to keep in mind, you have to switch off this tendency to think about functions of the complex numbers as being holomorphic, because these are very definitely not holomorphic. Right? And in fact, being holomorphic is equivalent to the decomposition only giving us the conformal part, the anticonformal part not existing. Yeah? Yeah? That's what we know, right? Because if satisfying Cauchy-Riemann equations is equivalent to balls being sent to balls, which is equivalent to just having the conformal part when we do the decomposition of matrices. Yeah? And just having the conformal part is equivalent to this thing being 0. Yeah? And this thing being 0 exactly does give us the Cauchy-Riemann equations, right? This is the first Cauchy-Riemann equation, this is the second Cauchy-Riemann equation. Yeah? So sometimes you see the Cauchy-Riemann equations being expressed just in terms of this. In terms of this z bar notation, right? So Cauchy-Riemann is equivalent to saying that df by dz bar is equal to 0, and that is saying that there is no anticonformal part to your gradient. The gradient is entirely conformal. Yeah? Cool. So all these things fit together pretty nicely. We also have, if I finally erase it, that if we do this algebra, so if we have that the Beltrami coefficient, this thing is less than kappa almost everywhere for kappa less than 1, then the algebra I was doing before, well, assuming that I got it right and the factor of 2 at the front disappears, the factor of 2 can be explained by this game here of going from matrices to complex numbers. But what is definitely true is that when we just formulate this like this, then f is kappa plus 1 over kappa minus 1 quasiconformal or quasi-regular. Yeah? And we saw this kind of expression in our calculation. I just had a 2 in front, right? But I think the 2 falls out somehow because of the identification between matrices and complex numbers. Yeah? But this is definitely the case. This is the right constant. Okay, so we can formulate stuff about quasi-regular, quasi-conformal mappings in terms of the Beltrami equation, in terms of the Beltrami coefficient, which is super useful for us. So, theorem. Measurable Riemann mapping. Okay. This is down to Murray, who's an American PDE guy from the mid and late 20th century, and a Polish guy called Bojaski, who was alive until quite recently. Actually, has been in Cincinnati, and yeah, nice man. All right, so measurable Riemann mappings, measurable Riemann mapping theorem. So given. So omega inside the complex numbers. And it has whatever. It's a nice domain, it has nice boundary. And a measurable function mu from omega into the complex numbers with the absolute value of mu is less than kappa almost everywhere for some kappa less than 1. Then there exists some f from the complex numbers to the complex numbers. F is locally Sobolev. It's W1, 2 locally, so on compact subdomains, and F is a principal solution which means that f of z is equal to z plus something that decays of order 1 over z for z near infinity, okay, such that it solves this Beltrami equation for this measurable guy, okay, such that df by dz bar is equal to mu df by dz almost everywhere, okay, that's what it does. So that is very powerful because how did we start to talk about the Beltrami coefficient? It's because we are interested in the Stoilow decomposition, right? So this is how the Stoilow decomposition goes. We have some domain omega. We have some quasi-regular mapping. Let's call it G. Okay. So then this is G of omega, right? And then since G is quasi-regular, we have that the Beltrami coefficient of G is strictly less than 1 almost everywhere. So now we're straight away going to talk about this in complex numbers, right? So G is Q, quasi-regular. So that means, so for some kappa which is between 0 and 1, we have that the Beltrami coefficient, we're going to write mu of G, is less than kappa almost everywhere. Yeah? And then we're going to use this Beltrami coefficient and we're going to solve the Beltrami equation with this, right? So find f such that we have df by dz bar is equal to this thing, df by, it solves exactly the same equation, right? Exactly the same Beltrami equation. Yeah. And then this f is quasiconformal mapping. I didn't add this, it follows on these hypotheses. It's this f, which is quasiconformal. This is an invertible mapping. Out towards infinity, it is flat, the derivative is always positive. By degree arguments, it's actually invertible, but this is part of the theorem. So there's this, and I should say, and f is quasiconformal. So it's actually depending on the k, so it's 1 plus k over 1 minus k quasiconformal. Yeah. So this f does this, right? It sends omega to f of omega. Okay. And I claim that we can find the mapping, which is holomorphic phi, from this to this, from f of omega to g of omega, by this. Define phi of, let's call it zeta, to be, so we pull back with f to the minus 1, which we can do because it's quasiconformal, it's invertible, and then we compose with g, so it's going to be g of f to the minus 1 of z. Yeah. Cool. So if we take the derivative of this guy, then what happens? Then we have d, okay, so now I'm going to identify everything as if it's 2 by 2 just for convenience. So I put the tilde on everything, it turns it into this 2 by 2 thing, right? So if we take the derivative of this thing, considered as 2 by 2, okay, this is now not a complex number, it's also it's now a vector, so I'm going to call it whatever, x. So this implies that this is equal to the derivative like this, f to the minus 1 of x, and then the derivative is just the chain rule, f to the minus 1 of x like this, but by calculus we actually know what this is. This is the derivative of f at f to the minus 1 of x inverted. No? Tilde. Everything is tilde. Turn this into 2 by 2. Yeah? Cool. So what I want you to do for next time is to think about this decomposition. Think about the fact that I've shown you that the Beltrami coefficient doesn't notice if we rotate the matrix and it doesn't notice if we dilate it. Yeah? Yeah? Think about expressing that fact that the Beltrami coefficient doesn't notice if we rotate and doesn't know if we dilate. Think about expressing this as the symmetric part of the matrix, in some way involving the symmetric part of the matrix, the symmetric part in the polar decomposition, right? So polar decomposition, again, we can write A as a rotation, which depends on A, and a symmetric matrix depends on A. And as I said, the symmetric part of the matrix records both the shape and the size, you know? Because it has this one extra coordinate, it's a three-dimensional thing, whereas Beltrami is two-dimensional. So think about expressing, some way of expressing the fact that we have two matrices A and B that deform things with the same shape, but with no constraint on the size or the rotation. Think about expressing this in terms of the coefficients, in terms of the polar decompositions of SA and SB. Think about some way of doing that, and apply what you've understood to this, okay? And if you work that through, what you should come up with is an understanding of why this thing, phi, is actually holomorphic. And if phi is holomorphic, then that gives us the Stoilow decomposition, because then we can just write the following. Just from this, we can compose on the, that should be zeta if I write it like this. Oops. Just from this, we can just compose on the inside with f of z, and we have that phi of f of z is equal to g of z, right? And if phi is holomorphic, then this is exactly the Stoilow decomposition we talked about. Yeah? So everything comes down to showing that this thing, which is certainly well defined, is actually holomorphic. Okay? Think about that for next time. Use this hint I gave you, and we'll talk about this on Monday. All right. Have a good day, people. See you on Monday. Bye-bye.